In this chapter, we will be discussing about various types of satellite, in that astronomy satellite, communication satellite, navigation satellite, weather satellite, earth observation satellite, reconnaissance satellite, types of orbits, geostationary orbits, sun synchronous orbits. Astronomy satellites. An astronomy satellite is basically really a big telescope floating in space. Because it is in an orbit above the earth, the satellite's vision is not clouded by any gases that make up the earth's atmosphere, and its infrared imaging equipment is not confused by the heat of the earth. Astronomy satellite therefore can see into the space up to 10 times better than a telescope of similar strength on earth. Can you guess what kind of things an astronomical satellite would be looking at? By analyzing the electromagnetic spectrum, the different wavelength of light, for example, ultraviolet, X-ray, visible spectrum, microwave and gamma rays, make a picture of something far away in space. So, the picture that come from Hubble or other astronomical satellite are not photographs but from a regular camera. Images created from the analysis of electromagnetic waves, the waves that make up the light spectrum. Astronomical satellites have many different applications. They can be used to make star maps. They can be used to study mysterious phenomena such as black holes and quarks. They can be used to take pictures of planets in the solar system. They can be used to make maps of different planetary surfaces. Astronomical satellites are different from space exploration satellites because they collect the data from the Earth orbit. Space exploration satellites are really probes that are sent out into the deep space. The Hubble Space Telescope is an example of an astronomy satellite. Communication satellites. Satellite communication in telecommunications, the use of artificial satellites to provide the communication links between various points on Earth's surface. Communications play a vital role in the global telecommunication system. Approximately 2000 artificial satellites orbiting Earth relay analog and digital signals carrying voice, video and data to and from one or many locations worldwide. Satellite communication has two main components: the ground segment, which consists of fixed or mobile transmission, reception and ancillary equipment, and the space segment, which primarily is the satellite itself. A typical satellite link involves the transmission or uplink of a signal from the Earth station to the satellite. The satellite then receives and amplifies the signal and retransmits it back to the Earth, where it is received and re-amplified by the Earth stations and terminals. Satellite receivers on the ground include direct to home, that is the DTH satellite equipment, mobile reception equipment in aircraft, satellite telephones and handheld devices. The satellite can have a passive role in communications, like bouncing signals from Earth back to another location on the Earth. On the other hand, some satellites carry electronic devices called transponders for receiving, amplifying and rebroadcasting signals to the Earth. Communication satellites are often in geostationary orbit. At high orbital altitude of 35,800 kilometers, a geostationary satellite orbits the Earth in the same amount of time it takes the Earth to revolve once. From the Earth, therefore, the satellite appears to be stationary, always above the same area of the Earth. The area to which it can transmit is called a satellite footprint. Communication satellites can also be in highly elliptical orbits. This type of orbit is roughly egg-shaped, with the Earth near the top of the egg. In a highly elliptical orbit, the satellite's velocity changes depending where it is in orbital path. When the satellite is in the part of its orbit that's close to the Earth, it moves faster because the Earth's gravitational pull is stronger. This means a communication satellite can be over the region of the Earth that is communicating with for the long part of its orbit. It will only be out of contact with the region when it quickly zips close by the Earth. Navigation satellites. Satellites for navigation were developed in the late 1950s as a direct result of ships needing to know exactly where they were at a given time. In the middle of the ocean or out of the sight of land, you can't find out your position accurately just by looking out the window. The idea of using satellites for navigation began with the launch of Sputnik 1 on October 4, 1957. Scientists at Johns Hopkins University Applied Physics Laboratory monitored that satellite. They noticed that when the transmitted radio frequency was plotted on a graph, a pattern was developed. This pattern was recognizable to scientists and it is known as Doppler effect. The Doppler effect is an apparent change of radio frequency as something that emits a signal in the form of waves passes by. Since the satellite was emitting a signal, scientists were able to show that the Doppler curve described the orbit of the satellite. Today, most navigation systems use time and distance to determine location. Early on, scientists recognized the principle that given velocity and the time required for radio signal to be transmitted between 2 points, the distance between the 2 points can be computed. The calculation must be done precisely, and the clocks in the satellite and in the ground-based receiver must be telling exactly the same time. They must be synchronized. If they are, the time it takes the signal to travel can be measured and then multiplied by the exact speed of light to obtain the distance between the two positions. The Navstar satellites are examples of satellites that use this principle. Weather satellites. As the name implies, these satellites are used for monitoring and forecasting of the weather. They can provide a much better understanding of weather phenomena. And because of this technology, you can find out weather conditions anywhere in the world at any time of the day. These satellites provide the meteorologist with scientific data to predict the weather conditions and are equipped with advanced instruments. Weather satellites can give information about the radiation measurements from the Earth's surface and atmosphere, which give information on the amount of heat and the energy being released from the Earth and its atmosphere. Satellites monitoring the amount of snow in winter, the movement of ice fields in the Arctic and Antarctic regions, and the depth of the ocean. Infrared sensors on satellite examine the crop conditions, areas of deforestation, and regions of drought. There are two basic types of weather satellites, those in geostationary orbit and those in the polar orbit, orbiting very high above the Earth at an altitude of 35,800 kilometers, that is the orbital altitude. Geostationary satellites orbit the Earth in the same amount of time it takes the Earth to revolve once from Earth. Therefore, the satellite appears to stay still always above the same area of the Earth. This orbit allows the satellite to monitor the same region all the time. Geostationary satellites usually measure in real time, meaning they transmit the photographs to the receiving system on the ground as soon as the camera takes the picture. A series of photographs from these satellites can be displayed in a sequence to produce a movie showing cloud movement. This allows the forecaster to watch the progress of large weather systems such as fronts, storms, and hurricanes. Forecasters can also find out the wind direction and the speed by monitoring the cloud movement. The other basic type of weather satellite is polar orbiting. This type of satellite orbits in a path that closely follows the Earth's meridian lines, passing over the north to south poles once every revolution. As the Earth rotates to the east to beneath the satellite, each pass of the satellite monitors a narrow area running from north to south to the west of the previous pass. These strips can be pieced together to produce a picture of larger area. Polar satellites circle at a much lower altitude at about 850 kilometers. This means the polar satellites can photograph clouds from closer than the high altitude geostationary satellite. Polar satellites therefore provide more detailed information about violent storms and cloud systems. Earth observation satellites. As you know, remote sensing is observing and measuring our Earth's environment from a distance. So, remote sensing or Earth observation satellites are usually put into space to monitor the resources that are important for humans. Remote sensing satellites are generally placed in the Sun synchronous orbit. Using these satellites, it is possible to see many features that are not obvious from the Earth's surface. Since these satellites are able to take images and observe areas all over the globe, the satellite is able to monitor areas in which the climate is very harsh or which are nearly impossible to reach by land. Reconnaissance satellite. These days, you hear about satellites for communication and scientific research. Some satellites, though, have far less public uses. Reconnaissance satellites are used to spy on the other countries. They provide intelligence information on the military activities of the foreign countries. These satellites can even detect missile launches or nuclear explosions in space. Reconnaissance satellites can pick up and record audio and radar transmissions while passing over a country. Finally, they can be used as an orbital weapon by placing warheads on the low orbit satellites to be launched at a ground target. This is not recommended or frequently the use of the satellites. There are basically 4 types of reconnaissance satellite. First, they are optical imaging satellite that have light sensor to detect missile launch and see enemy weapons on the ground. Next are the radar imaging satellites. They are able to observe the Earth using the radar technology through cloud cover. Third, they are signal intelligence or ferret satellite that are essentially super sophisticated radio receiver that capture the radio and microwave transmission emitted from any country on the Earth. Finally, there are relay satellites that make military satellite communication around the globe much faster by transmitting data from spy satellites to stations on Earth. Starting in the 1960s, the United States began launching many series of reconnaissance satellites. The first series was called Discover, and as these satellites circled the Earth in polar orbits, they took pictures. The next series of US spy satellite was given the code name Keyhole or KH for short. They mostly did routine surveillance or weapon targeting in a low 80-mile orbit. They either took wide area pictures of large land masses or took close-up pictures of special interest objects. There are 4 types of reconnaissance satellites. Optical imaging satellites that have light sensors that can detect missile launches and locate enemy weapons on the ground. Radar imaging satellites which are able to observe the Earth using the radar technology through cloud cover. Signal intelligence or ferret satellites that are essentially super sophisticated radio receivers that capture the radio and microwave transmissions emitted from any country on the Earth. Relay satellites that make military satellite communications around the globe much faster by transmitting data from spy satellites to stations on the Earth. Types of orbits. Any object that moves around the Earth has an orbit. An orbit is a path that a satellite follows as it revolves round the Earth. The plane in which a satellite always moves is called the orbital plane. The time taken for completing one orbit is called orbital period. Orbit is defined by 3 factors: shape of the orbit, which can be either circular or elliptical depending upon the eccentricity that gives the shape of the orbit; altitude of the orbit, which remains constant for a circular orbit but changes continuously for an elliptical orbit; and the angle that an orbital plane makes with the equator. Depending upon the angle between the orbital plane and equator, orbits can be categorized into 3 types: equatorial, inclined and polar orbits. If the angle known as orbital inclination is 0 or 180 degrees, then the orbital plane lies in the equatorial plane and the orbit is called the equatorial orbit. When the angle is 90 degrees, the satellite moves over the north and south pole and the orbit is called the polar orbit. However, An orbit with inclination close to 90 degrees is called a near polar orbit. There could be different orbits having inclination between 0 or 90, which are known as inclined orbits. The time taken for a sensor to complete tracing or imaging of almost the entire Earth before it starts tracing the same area for a second time is known as orbital cycle. The exact length of time of orbital cycle varies with each satellite. It is also important to note that an orbit that brings the satellite over the poles or close to them has a larger angle, but an orbit that makes the satellite stay close to equator has smaller angle. As a consequence, the distance away from the Earth will affect the speed of the object in orbit. So, the orbit selection can vary in terms of altitude above the surface of the Earth and the orientation and the rotation of the orbits relative to the Earth. There are different types of closed orbits used for operating various satellites. Most commonly used satellites are geosynchronous orbits, sun-synchronous orbits, geostationary orbits. It is the west to east equatorial orbit in which a satellite is placed on the equator, that is the 0 degrees latitude orbital plane at an altitude of about 36,000 kilometers above the Earth's surface. At this altitude, satellites travel in this orbit with the same speed and the direction as the Earth. The geosynchronous orbit is an orbit which has the orbital period that matches the Earth's sidereal rotation period. The synchronization of rotation and orbital period means that the observer on the surface of the Earth, the satellite, appears to constantly hover the same medium north to south line on the surface, moving in the slow oscillation alternatively north and south with a period of 1 day. So, it returns to the exact same place in the sky at exactly the same time each day. There is a special case of a geosynchronous orbit which is known as the geostationary orbit. This is a geosynchronous orbit that is circular and zero inclination, that is directly above the equator. As a result, the satellite remains stationary vertically above a fixed point on the Earth's surface. Hence, the relative to any location on Earth, the position of the satellites remains stationary. This orbit is called geostationary orbit, and the satellites revolving in this orbit is called a geostationary satellite. The geostationary satellite takes 24 hours time to complete one orbit around the Earth, which is also the same time period for the Earth's rotation. This is why to people on the ground, the geostationary satellites appear to be motionless and at a fixed position in the sky. Any sensor system on the geostationary satellites view the same area at all time. This is much higher orbit in which satellite takes a lot more energy to reach. At this altitude, satellites have a view of almost an entire of one hemisphere. Resolutions of imagery from geostationary are very coarse. It provides distorted images of a polar region with poor spatial resolution. For this reason, imaging and mapping satellites are not geosynchronous. Thus, communication and weather purposes are the most common use of geostationary orbits. Communication satellites are often given geostationary orbits or close to geostationary, so that the satellite antennas that communicate with them do not have to move but can be pointed permanently at a fixed location in the sky where the satellite appears. Geostationary satellites provide a large coverage which is useful for monitoring deadly local storms and tropical cyclones. Since these satellites continuously view same scene, as a consequence, these are ideal to study the dynamic phenomena such as cyclonic movement, cloud motion, etc. Advantages of geostationary orbits are following. Large spatial coverage. Geostationary satellites are enough to cover all the non-polar regions of the Earth. One satellite can cover almost 1/3 of the Earth's surface. Permanent visibility of the satellite, allowing continuous telecommunication and high rate of repetition for observation. One ground segment is enough for the satellite monitoring. Polar orbits. Polar orbits have an inclination of 90 degrees with respect to the equatorial plane of the Earth. A polar orbit is a satellite orbit that passes close to both the poles of the Earth. As the name suggests, the polar orbits passes over the Earth's polar region from the north to south. During a 12-hour day, a satellite in such an orbit can observe all points on the Earth. The satellite moving in a polar orbit is called a polar satellite. Satellites which follow the same orbit. The Earth rotates underneath and allows satellite to see virtually every part of the Earth. It takes approximately 90 minutes for the satellite to complete one orbit. These satellites pass over the equator at the same solar time every single day, which allows it to collect data consistently. The orbit are low altitude orbits between 200 and 1000 kilometers above the Earth. The satellite offers the best views of the planet, particularly of areas that are often difficult to cover. Polar orbit satellites are used for reconnaissance and Earth observation. They are also used for measuring ozone concentration in the stratosphere or measuring the temperature in the atmosphere. Polar orbits are also sometimes used for weather satellites. Ideally, all satellite images should be acquired under uniform illumination conditions, so that features present in the image of same area taken on different data shows the changes in the ground conditions rather than change in the condition of observation. However, in reality, satellite images of different data varies because of differences in latitude, time of day and seasons, resulting into different illumination conditions. Sun synchronous orbits. When the orbits are designed in such a way that the satellite orientation is fixed relative to the Sun throughout the year, such orbits are called sun synchronous orbits. These orbits are designed to remove one source of variation in illumination, which is caused by differences in time of day. The satellite in sun synchronous orbit passes over a given part of the Earth at roughly the same local time of day, though not necessarily every day. In other words, whether the satellite observes a given ground scene, the Sun is always in the same location in the sky. Since there are 365 days in a year and 360 degrees in a circle, it means that the satellite in this orbit has to shift its orbit by approximately 1 degree per day. The satellite orbiting in this orbit is called a sun synchronous satellite. Sun synchronous satellite flies at an altitude between 700 to 800 kilometers with an orbital period between 90 and 110 minutes. Satellites in sun synchronous orbits passes from north pole to south pole on a sun-lit side, the descending node, and from south to north on a shadowed side, the ascending node. Sensors that depend upon the solar radiation acquire images only during the descending pass, but other sensors can acquire data independently during both the passes. Sun synchronous orbits are particularly useful for missions that acquire images of the Earth because shadows from objects at a given location on the Earth's surface are always cast from the same angle. This simplifies the comparison of images taken on different days to detect changes. Satellites in this orbit are often placed at low altitude so that they provide complete coverage of Earth's surface at least once per day. Remote sensing and meteorologically satellites are placed in the sun synchronous orbits. Orbu, QuickBird, Iconos, Spot, Landsat, ERS, RadarSat, etc. are examples of satellites orbiting in sun synchronous orbit. Dawn to dusk orbit is a special case of sun synchronous orbit in which the orbital plane of the satellite coincides with the plane that divides the half of the Earth that is illuminated by the Sun from the half that is dark. If the plane were aligned slightly different, the satellite would spend half of its time in full sunlight and half in shadow, but a dawn to dusk orbit allows the satellite to always have its solar panels illuminated by the Sun. For example, the Canadian RadarSat Earth observation satellite use such dawn to dusk orbits to keep their solar panels facing constantly. So, they can rely primarily on solar power rather than batteries. Summary: the Astronomy satellite is basically really a big telescope floating in space where we can see through the space objects 10 times larger. Satellite communication plays a vital role in global telecommunication systems. Navigation satellites are those satellites where it is used to determine the location by using time and distance method. Weather satellites are used for monitoring and forecasting of the weather. Earth observation satellites are usually put into space to monitor the resources that are important to humans. Reconnaissance satellites are used to spy on other countries. An orbit is a path that a satellite follows as it revolves around the Earth. A geosynchronous orbit is an orbit which has an orbital period that matches the Earth's sidereal rotation period. When the orbits are designed in such a way the satellite's orientation is fixed relative to the Sun throughout the years, such orbits are called sun synchronous orbits.